Welcome to another edition of Research Connection. With me today is Dr. Will Love. Thanks for joining me, Dr. Love.
It's my pleasure.
So tell us a little bit about yourself.
So I'm a veterinarian. I practiced for a couple years and then decided to come back to academia. I got my MPVM and PhD from Davis, and I joined Dr. Lanzas' lab as a postdoc in middle of 2015. And so our research has been focused on a concept called collateral resistance, which is kind of getting a lot of interest in antimicrobial resistance research. So we usually understand that antimicrobial resistance is the product of natural selection. If you use a drug repeatedly in a population of bacteria, that population of bacteria will develop resistance to that antibiotic. What collateral resistance shows, what it describes is when you can have resistance traits, for example, ampicillin resistance and tetracycline resistance. These are drugs that act in completely different mechanisms at completely different sites of action in the cell's machinery. But if the genes for these resistance traits become linked and you tend to have correlation of these traits in the population, you get a situation where using ampicillin will not only select for increased ampicillin resistance, but it can also select for more tetracycline resistance, which leads to a degree of uncertainty about what drugs you're using are going to impact the resistance in your populations. So in this slide, you can see a representation of a population where you have the gene for ampicillin resistance is orange and the gene for tetracycline resistance is green. And in this population, the genes are not correlated with each other. They're not, meaning they're not appearing together any more likely than you would see by random chance. So when you use ampicillin, if you get rid of all the ampicillin resistant or all the ampicillin susceptible bacteria, you're left with ones that are only ampicillin resistant. The prevalence of ampicillin resistance goes from 50% to 100%. The tetracycline resistance stays the same, though, going from 50% to 50%. Now, in this different population, we have the traits that are correlated with a coefficient of 0.75. So these are pretty tightly correlated. But again, you only have 50% ampicillin resistance and 50% tetracycline resistance in the initial population. Now, when you remove all the tetracycline susceptible bacteria, not only does your ampicillin resistance go from 50 to 100%, your tetracycline resistance has gone from 50 to about 88%. So even though we've used a drug that has nothing to do with how tetracycline works, again, these have completely different mechanisms of action, we've substantially increased the amount of tetracycline resistance in the population. So when you just have two antimicrobials like this, it's not that hard to understand these correlations. But the problem becomes when we start looking at the number of antimicrobials that we're testing for at the diagnostic lab. You'll frequently get a panel of like 15 different drugs. When you have two traits you're looking at, you only have one correlation to test. When you have 15 to test, you have 105 pairwise correlations that you have to look at. So we needed a method to not only estimate which correlations were real and which ones were spurious, but also do so without the null hypothesis testing that we're used to in statistics. And so the method we've developed uses networks, graphical models, to represent all this. So not only would you have to not only would we have to evaluate 105 different correlations, we would have to communicate that back to the clinicians and to the researchers. And looking at a correlation matrix with 105 entries is tedious, to say the least. So what we found is that there's a method that's been recently described called the graphical lasso. When there's no correlation, the nodes in the network are not connected by a line. If there's a weak correlation, after we apply the graphical lasso, there's a dashed line. And if there's a strong correlation between them, meaning it's likely that you're going to have collateral resistance and indirect selection, there's a bolder line. We can get a really informative picture of what's going on and how these resistance traits are interacting with each other and how they group together using a system like this. So moving forward, one of the things that we want to do is find the genetic mechanisms that are providing for the correlations. So one of our collaborations is with, we've recently resubmitted a grant, a Morris Animal Foundation grant with Dr. Peng, Dr. Jacob, and our Lanzas lab to take isolates that have been collected and genotyped by have been genotyped for methicillin resistance by Dr. Jacob, and genotype or do a whole genome sequencing with Dr. Peng, and try to identify these genetic elements that are responsible for the correlations.
Thanks for joining me.
No, like I said, it's been my pleasure. Thanks for having me.
Yeah, best of luck.
Thanks.